This is the collaboration with many people. First part is joint with Fourier, Ghislain Fourier and Anne Schilling. And the second part is collaboration with Cédric Lecouvet and Marc Shimozono. And today, as Anne already mentioned, we have some distinguished family for quantum affine algebra, UQG. This is quantum affine algebra. There is a distinguished family of irreducible finite dimensional module, which is called, which I want to write WRSA, which is called Kirillov-Reshetikhin module. And there was a conjecture that for suitable A, there is 3 parameters, and R and S are the same as I mentioned. But for KR module, there is another some parameter in Q. And for suitable A, there exists crystal basis in the sense of Kashiwara. And actually, I write the theorem already mentioned. For G, non-exceptional. There exists for suitable A. This KR module RSA, since this is specified, maybe a dagger, has a crystal basis. Which we want to denote it by RS. Okay, and let me review. R corresponds to the Dynkin nodes of the Dynkin diagram. Except 0, or maybe you can say that the Dynkin nodes of Dynkin diagram for corresponding finite dimensional simple Lie algebra, and S is just the positive integer. Okay, and there is again a theorem by KMN. I can tell all the names of all the authors, but anyway, well, I want to consider consider the perfectness of KR crystals, and there is a theorem by KMN square. If B, there is a notion, of perfect. But I want to go into detail about the correct definition, precise definition of this perfectness. Maybe you can consult famous Hong Kang's book. Yeah. So there is a notion of perfectness, and if some regular, maybe finite crystal is perfect, and there is also a notion of level S, okay, then you have the following isomorphism of crystals. So you have B lambda times we tensor this regular crystal becomes again some highest weight crystal. I'll mention I'll define the notations. For any lambda is the dominant integral weight of level S. So for any dominant integral weight lambda, there exists again dominant integral weight So this is determined by lambda of the same level. And you have this isomorphism of crystals as UQG crystal. And I again, let me define. So this is, maybe you already know, this is the highest weight crystal or highest weight crystal of highest weight lambda specified here, highest weight lambda. Okay, so you have this isomorphism of crystal. Yeah, so this is the property which I want to use in this talk. And our next theorem by Fourier, myself and Schilling, is that we consider so since we have obtained these KR crystals and we already established the explicit crystal structure of these crystals, we next proceed to check whether it is perfect or not. And the answer is, of course, again, you have this condition, non-exceptional. Then the answer is BRS is perfect. Perfect. If and only if it is allowed by a so-called X equal M conjecture. Okay. And I don't want to go into detail about what is X equal M conjecture. This is some conjecture related to polynomials. So one side, this is called one-dimensional sum, and the other side is called fermionic formula. And this comes from some technique in integrable lattice models. And this also comes from another technique called Bethe-Ansatz in the integrable models. And there is a conjecture that these polynomials are the same. Yeah? And to be more precise, in particular, so I want to focus on type D. So maybe this next statement would be enough. So BRS is perfect of level S for any R. For any R. For any R. So level is the same as this second index. Any R. When as long as we consider non-exceptional Lie algebra, when G is simply raised A or D, or twisted cases, always any crystal is perfect. Okay, but for type B or C, for some R and for some S, it's not perfect, or such a thing happens. Okay, so since we have such a theorem, so we have sort of harvested the very important crystals. So next, what we want to do next is to cook and eat. Okay, so first one, I want to split, so which we call row splitting. So how does this mean? What does that mean? So sometimes the Kirchhoff-Lechtin crystal is written graphically like this, drawn graphically like this. So this is because for type A, this KRS is isomorphic to B rectangle R by S rectangle, okay, as a classical AN crystal. And such a Young diagram corresponds to the highest weight. And this means that this is, again, irreducible with respect to classical AN crystal. Yeah? So usually we can represent a crystal like this, R by S rectangle. Okay? So I want to split here. I want to split. So which we want to call row splitting. And second one, I want to introduce some involution, global involution, sigma, on maybe Ann's terminology. It's is it also promotion? But anyway, we want to some automorphism on KR crystal satisfying this property. EI is equal to E. This E is the casual operator. Since we only consider a crystal, not module, so this is crystal operators. For any. Okay. So if you draw a Dinkin diagram, usually there is no ambiguity how to draw a Dinkin diagram for type D. So in this talk, I want to concentrate on type D. Since these properties, these facts are already known for type A. So I want to talk about type D. So for type A, type A, such similar facts are already known. So I want to concentrate on type D. Okay, and usually we draw and label nodes like this. Okay, then this automorphism corresponds to just so turn this over, right? Something like that. Rotate 180 degrees. So I want to construct such an automorphism. And actually, I think this is important for for type A. The X equal M conjecture, which I mentioned here, is already proven completely. And there is some technique which they use the X equal M conjecture settled by Kirillov, Schilling, Shimodono. And one of the main techniques used there is split, like this, split these KR crystals. But they use, instead of row splitting, they use column splitting or box splitting or something like this. But yeah, I think you can prove using row splitting. Yeah. There are for type A, there are many duality. I think row splitting, you can use row splitting for such a proof. So for type D, this conjecture is still open, except for some special cases. So one of my hope is to use these technique for proving these conjectures in full generality. So, and one of the motivation here is so there is another conjecture which is called X equal K, and by Shimozono, Zabrocki, which asserts, roughly speaking, that if rank n is sufficiently large, then the x side one-dimensional sum here is a sum of one-dimensional sum and one-dimensional sum of type A plus some little Richardson coefficient. So there is such a conjecture, and probably we hope, or almost it's settled, but only this morning Cedric Lecouvreur showed that there is some problem in his proof. It's part of his proof, but I hope it's not so serious. But anyway, to show, I hope sigma is or will be, or I don't know, used to show this conjecture. Okay, so these are motivations. And I want to use these perfect properties to construct these two things. So I will begin with the first one. So we consider this highest weight crystal, and we tensor. Okay, and lambda 0 is the usual notation by Katz, which is the zeroth fundamental weight. Or maybe I just define lambda I be the ith fundamental weight. Then we already know that what is the this right-hand side, okay? And the answer is for any s, you have this weight r bar. What is r bar? R bar is the residue with respect modulo 2. So a bar is just the mod 2 equal, and a bar is 1 or 0. Okay, it's just residue. Okay, so we already know this fact by the previous theorem, and we again use the similar kind of isomorphism in an opposite way. So we have again B S R minus 1 bar times B oneness. Okay, this is also this isomorphism also correct. Okay, and just forget about this, and I again use similar opposite isomorphism. Then we get this one. So I have these isomorphisms. Then you have this the connecting these isomorphisms. We have a map from here. Map here from here, from here to here. Okay. So now it's rather easy to obtain. Maybe you already imagine what is this. How do you define this splitting? Okay. So this corresponds to the tensor product. You associate some element of BRS with the 2 R minus 1 times 1. Yeah. So by this isomorphism. So actually you consider this element, and this is a highest weight vector here in this highest weight crystal. This is the highest weight vector in B S0, and this is any element of BRS. And from the map, you have some element here, U in the highest weight crystal times B1 times B2. Okay. Then the first lemma is this becomes again highest weighted. So you call U S. Then you can define a map. So if you admit this, you can define. Maybe I write in a theorem. Theorem. First theorem is the map given by associating B associating to B this tensor product. So I want to call this SR, law splitting. BRS goes to BR minus 1S times S. Satisfies this commutes with the Kashiwara operators for when I is not equal to 0 first. I'll explain a bit later. EIB is equal to EISRB if for I. And for zero arrow, zeroth Kashiwara operator, you have this. For with some condition. For B, this is for any B, but this is for and for any B, and for some for B, such that epsilon 0 is greater than S. S is the level of this crystal. Okay. And the proof is very easy. Since this is the zeroth fundamental weight, you can if I is not equal to 0, you can apply E0 on both sides. But since this is just 0, so this action just go through these highest weight vectors, and you have this. But for 0, for I equals 0, since there is this highest weight, so there's a condition. There should be a condition that the application of Kashiwara operators actually the Kashiwara operators actually applies to this. Yeah. So we both apply E0 on both sides. And this already know that that's highest weight, but you need some condition that this go through this and actually applies to the second component. So that's a condition. So you understand this isomorphism, the series of isomorphisms. This is immediate. Okay, and if there is enough time, I want to give a sketch of proof, but Mark says that this is only this morning. Mark said that this fact is already in his previous paper. But anyway, so maybe I can give how to prove this. It's not so difficult. So I'll just sketch of this lemma. So maybe we have to recall the decomposition or characters of this KR crystal. In this type D case, and maybe we need to assume that R is not a so-called spin node. So we assume that R is 1 or up to 2. So this is a rather special node, so I don't want to deal with these one. Okay. Then this decomposes into these highest weight crystals as DN classical crystal. These highest weights are identified with Young diagram or partition, yeah, in a usual way, like type A. The condition is lambda is obtained by removing horizontal dominoes. Removing horizontal, maybe I just draw this one. Okay. Maybe I give you some simple example. For 2, you first. Oh, this is not well defined. Sorry. By removing from obtained by from rectangle, this R by S rectangle. So we first consider 4 by 2 rectangle. 4 by 2 rectangle. No, not good. Okay, 4 by 2 rectangle. And we list all possible Young diagrams obtained by removing these dominoes. So you have, I don't write B, just write the partition. So you have this, the biggest one. This one, this one, and this one. What's left? Time 5. Yeah, that's classical decomposition. I assume. Theorem? Yeah, maybe. Yeah. Thank you. But you know, we assume the similar. We can do similar technique because even if you have these cases, then you have similar isomorphism. But yeah, as Anne says, what I checked is just not a special case. So I assume this. Okay. So I'm just continuing the sketch of proof of this lemma, but just B lambda, be the Dn classical highest element, highest weight vector in B lambda. Lambda appearing in such decompositions. Okay. Then, let's see. Then to show this, it's enough. So again, we consider this isomorphism. So first, so there is a very standard element in both sides, which is the highest weight vector. Since both are isomorphic to some highest weight crystal, R bar, so there must be a unique highest weight vector here and also here. So first, I calculate these highest weight vectors. So in this side, in left side, the highest weight vector here is a fine highest weight vector, given by U S lambda times phi. What is phi? Phi is the unique element unique element in B5. So, in this proof, let me just assume that R is even. All these are similar, but just let me. So if R is odd, you always have this component. So and there is only one element here, so this is a unique element in. Yeah? So this is the highest weight vector in left side, and on this right side there is a unique element, and which is given by 1s times 1 bar s. And what is 1 s times and 1 bar s times? And this is actually the representation by a Kashiwara-Nakashima tableau. So these are Kashiwara-Nakashima tableau. So this is an element of BR-1s, and this is an element of B1s. And B1s is irreducible because you cannot remove any horizontal domino. So this is irreducible also for classical DN crystal. So since this is a classical, just DN crystal, not affine DN crystal, you have Kashiwara-Nakashima tableau. So this is the representation by this tableau. So this is just the 1 bar continues S times. Yeah, it's a tableau like this. I just abbreviate like this, S1 bar. So for type A, you only have 1 to n. As letters, you only have 1 to n. But for type D, you have barred letters also. Okay? And since I assumed R is even, R-1 is odd. And you can easily see that when this index is odd, this contains this component always. So again, this is an Kashiwara-Nakashima tableau representation of this such element in this component. Okay? So this is the highest element. Then I think it's easy to. So what you are left is to show that apply. So apply. So these correspond to each other. So next thing you need to do, apply suitable sequence of Kashiwara Fi operators on both sides. To get something like, so applying a suitable sequence of Kashiwara operators, you in principle, because they are connected, you in principle get to arrive at B lambda. Yeah? Corresponds to U as something. And you can actually do this calculation explicitly. And maybe as an example, I give, so when R is even, then if the highest weight is given by this partition, then the answer is B1 is B of So this is again a highest weight vector in this crystal. Okay, times B1, B2 is it's rather complicated, but lambda something like this, and these are signatures of this partition, and so on, and R lambda R, and S minus lambda 2. Okay. which is belongs to B again. So this is D. Okay, and since both the highest times BRS and the highest times these crystal elements, they are invariant under action of non-zero Casual operators. So once you get the highest classical highest weight vectors, this are again any element is that does not go. This is trivial. So this is enough to check the lemma. Okay, that's the way how we just see. Okay, so my time is 20 minutes. So next I explain how to construct this sigma. Okay. So, but this is the technique is very similar, so you can easily imagine how I construct sigma. So it's very similar. So first, again, I consider this tensor product. Then, as I explained, this is isomorphic to R bar. Okay. Then at this level, I apply Dinkin automorphism. So I construct a map from this to n minus R bar. So this is the n or n minus bar depending on whether R is even or odd. Okay. How do we construct this map? It is just by Dinkin diagram automorphism. So you can express any element in this crystal by applying F on highest weight vector. Okay? Then since this is affine highest weight crystal, and as you see, the Dinkin diagram is completely symmetric. So there is a canonical map from here to up n minus I. And just subtract from n these indices. And you again consider highest weight, but here on this in this highest weight crystal. And this is a well-defined map, a bijection. And again, we consider we want to decouple into these two pieces. So we have then again you can construct from here to here. You again have a map. Okay. So, and again you consider U S lambda 0 times B, and this goes, assume this goes to U S, U times B, say, prime. Then the first lemma. First lemma is again, this U again is U S lambda n. What is it? N. Yeah, highest weight. Then again, you can define B1 to be sigma B. Okay. And I want to show that commutes, this map commutes with casual operators modulo linking automorphism. But by definition, it's clear. By definition, it's clear that if, again, I is not equal to 0, you have this one. If for I not equal to any. This is easy. Because, again, so this element corresponds, and we can apply E0 this side, and since we flipped by linking auto, so we can apply En. But En minus I. But since EI, if I is not equal to 0, always this operator forget about this and goes to the second component. So you immediately obtain this. But if you want to consider 0 action, then you have some care or attention. Okay. So again, you need some condition that the action of E0 or En applies to the second component, which is equivalent to saying that B such that epsilon 0. And the theorem is that in fact, you can remove this condition. So actually, this holds for any B. So this is the theorem. So from this condition, you don't know this. If you forget about this condition, this you don't know whether this holds or not. But by direct calculation, I'll show you have. Here you need some calculation, some brute force. Okay, so this is the theorem. So actually, the rest of the talk is just some technical details how to show this. But maybe, yeah, since there is still some time, I'll show how. I'll sketch how to prove this. But maybe the important point is that we already have some other automorphisms, tau prime. In previous papers with An, we used the sigma for in the other meaning, and that is actually a tau here. But anyway, don't confuse. Anyway. Again, I write the linking diagram of Dn. Okay. Then here is some symmetry here, and I denote by a tau. Yeah, and here you have another symmetry here, and I denote it by tau prime. And what does that mean? Actually, we already have two automorphisms, tau and tau prime on BS RS, satisfying here satisfying tau satisfies E0 is like this. Okay, and if we change 1, we have 0. So it's switching 0 and 2. Yeah, and the tau EZI is equal to I tau for any I not equal to 0, 1. Yeah. So we already have such automorphism on this KR crystal satisfying these conditions. Okay? This is already constructed by Schilling for construction of the combinatorial KR crystal of type D. And this part is not so difficult. This is nothing to do with the description of automorphism is similar, yeah? But let me be more precise. You have n is equal to n minus 1, and n minus 1, n, ei, when I is not equal to n or n. And this is easy. This is easy. Or some classical matter, or maybe. Since this is nothing to do with affine structure, so this is already known. And at the Kashiwara-Nakashima tableau level, it's just exchanging x and x bar. And I use these two automorphisms to show our theorem for sigma. So lemma, my second lemma. For any dn minus 1 highest weight element. dn minus 1, I specify dn minus 1 to be this Lie algebra or quantum algebra corresponding to this Dynkin diagram. So we ignore 1, then this is the Dynkin diagram of dn minus 1. And by this, I mean dn minus 1 by this Levy sub algebra. I don't know. Okay. So then, explicitly, I can write this, the condition. This is just the these are killed by Kashiwara operator by with 2, 3, and yeah. So this corresponds to these nodes. Now for any dn minus 1 highest element, B in BRS, we have sigma tau B is tau B. So I have this lemma. And the proof of this lemma is very technical, and I don't want to go into detail. But in any case, you can do it by hand. And then once you admit this theorem, you can prove this theorem. Actually, we can to prove the theorem. It's enough to show similar relation for any B. So, namely, it's enough to show the same relation. Actually, same for any B in this element in this crystal. So because this is very easy, so it's just the sequence of relation. Just follow using relations which already established. So we have for any element you have this one, so you can exchange sigma tau E0. But you can exchange this T1 tau, yeah, and you can we want to show the commutativity of 0 only, but the other commutativity, I should not say commutativity, but anyway, the relation for not equal to 0, it's already established. So you can exchange like this. Okay. Then again, you exchange this, tau prime sigma, and you exchange tau en. But these are automorphism. You can remove these. So sigma. It's done. Yeah. So you from using this lemma, if you can prove this relation, the same relation for any b, it's done. But this is also, to prove this is also easy. So since it's a b for any b, we can always for any b we can find some d n minus 1 highest element b0 and sequence I maybe bar or maybe I1 IL. Yeah, and these components should belong to this set. So these numbers should be between 2 and n, greater than or equal to 2, such that B is EI bar. So by this notation, I mean just the application, the product of this B0. Yeah, because it's just the highest weight vector, and any element or it can be expressed by just applying F. Okay. And next we calculate left side and right side independently. B for any, but you have this relation sigma tau Fi B. Okay, but the tau intertwines. You can exchange F, and by you have again you have similar automorphism on letters. If you considering tau, that tau sends 0 to 1 or 1 to 0, and tau I is I when I is not equal to 0, 1. Yeah, so you can easily extend this definition to sequence letters. Then you have this I bar. You understand the meaning of this. Each letter is changed like this. Okay. And again, you have sigma tau. Yeah. And the point is that the since this sequence contains does not contain 0 or 1, in this sequence there is no 0 or 1 in this sequence. So you can again exchange, because if you use this is prohibited, because that's the relation we want to show. So you cannot use this. Yeah, but because we took dn minus 1 highest element, there is no 0 in this sequence. So we can exchange, and you get this. Yeah, and you can apply similar thing. And but maybe you easily see that for any I, sequence I, these are actually the same. Yeah, so it's done. Yeah. So it's all. And yeah, maybe yeah, I already finished the main point. So I finish.